Interest in plant-based protein is increasing. Millers are interested in exploring nitrogen management strategies which might increase grain protein of oat without increasing lodging and reducing test weights below acceptance for milling. Late-season applications of nitrogen, either at the boot stage or later, are well documented to increase grain protein in wheat. Dribble banding UAN is an effective way to apply late-season applications of nitrogen, provided adequate and timely rainfall is received after application. Well, maybe that's a little too much rain. Dribble banding typically causes less leaf burn than foliar broadcast sprays, and is still an effective way to apply nitrogen, as most of the nitrogen is taken up by the roots and little is absorbed by the foliage. Late-season applications of 30 pounds of nitrogen per acre typically increase wheat grain protein by about 0.5% on average in Western Canada. Split-applying nitrogen has also been reported to reduce the risk of lodging in wheat. Work by Wu et al. Found delaying application of half of the nitrogen until after jointing increased lodging resistance, increased grain protein, and maintained yield potential relative to applying all the nitrogen at seeding. Side-banding environmentally smart nitrogen is another way to supply late-season nitrogen, as it takes time for the polymer coating around each granule of fertilizer to break down and release the nitrogen. The impact of late-season nitrogen on oat grain protein, lodging, and test weight stability is less well researched. This study will determine if split-applying nitrogen or the use of ESN can increase grain protein, reduce lodging, and still maintain yield and test weight of milling oat. Determining how to increase oat grain protein without increasing lodging or reducing test weight is of interest to oat millers and producers. If oat protein can be effectively managed, millers may be willing to incentivize oat producers by offering protein premiums in the future. The trial is conducted in 2025 at these 7 AgriArm locations. Here's the complete treatment list. The first 4 treatments were analyzed separately to determine if there was a significant response to increasing rate of soil plus fertilizer N. If the site is unresponsive, then the effects of nitrogen management cannot be properly determined. Treatments 3 to 10 were analyzed as a 2x3 factorial. The first factor is total nitrogen, which is either 110 or 140 pounds per acre of soil plus fertilizer N. Our second factor has 3 levels of nitrogen management. Treatments 3, 5, 6, and 9 all have a total of 110 pounds per acre of soil plus fertilizer nitrogen. For treatment 3, all the nitrogen has been applied as urea in the sideband. Treatments 5 and 6 are both receiving 30 pounds of nitrogen per acre of dribble-banded UAN. Treatment 5 was at the 4-leaf stage, and treatment 6 was at the boot stage. We expect the later application to favor grain protein over yield. Treatment 9 is applying 30 pounds of nitrogen per acre of ESN in the sideband. Treatments 4, 7, 8, and 10 follow the same pattern, but are at a higher N level of 140 pounds per acre. Okay, let's dig into the results. When combining all sites, increasing the rate of side-banded nitrogen significantly increased oat yield in the blue bars and grain protein as represented by the orange dots. However, when analyzed individually, not all sites were responsive. Yield and protein responses were not detected at Yorkton and Prince Albert. Effects on grain protein were also insignificant at Swift Current. Background soil nitrogen was high and yield potential was relatively low at all of these unresponsive locations. In addition, lodging was high at Yorkton and Prince Albert, which likely created a lot of unwanted variability. With all sites combined, we didn't detect a significant impact of nitrogen management on yield or protein at the 110 pound of nitrogen per acre level. The same was true at a total nitrogen level of 140 pounds per acre. However, for the protein data, there were several interactions with site. When looking at the sites individually, yields were lower at Indian Head when a portion of the total nitrogen was supplied with the side-banded ESN or dribble-banded UAN at the 4-leaf stage. Grain protein was also significantly reduced at this site by 0.28% when UAN was applied at the boot. These yield and protein losses may have been the result of an excessive delay in nitrogen release from the ESN or environmental conditions which stranded UAN in the dry soil or enhanced ammonia volatilization. This highlights the environmental risks associated with split applications of UAN. Those of you with a keen eye may be confused by the change in the base rates and total nitrogen expressed in this figure. Essentially, this data represents the average of 110 and 140 pounds per acre of total N. In other words, every treatment here represents a total of 125 pounds of nitrogen per acre on average. At Yorkton, a significant nitrogen by management interaction found the use of ESN significantly increased grain protein, but only at the 140 pound per acre level of nitrogen. While the reason for this inconsistency is unclear, ESN is known to increase grain protein by delaying the release of nitrogen. At Redvers, applying UAN at the boot stage significantly increased grain protein by 0.33% when averaged over nitrogen levels, compared to sidebanding all the nitrogen. Again, late-season application of nitrogen is known to favor the development of protein. At Scott and Melfort, management did not significantly affect grain protein averaged over nitrogen levels, even though these sites were responsive to increasing nitrogen. This is Scott. There are no significant effects of nitrogen management on either yield or protein. However, I had to adjust my protein scale because the grain proteins are very high, implying that there was lots of background nitrogen at this site. This is Melfort. Again, no significant effect of nitrogen management on either yield or grain protein. I had to adjust my scales again because the yields were high and the protein was low. While the study found some examples of where nitrogen management could maintain yield and increase grain protein, the effects were inconsistent between sites and even between total nitrogen levels within sites. I won't bother to show you the lodging data because the effects of management were largely insignificant, whether lodging levels were high or low. Let's switch to test weights as represented by the green bars. To give you an idea of whether the test weights are good or bad, I've placed a red arrow at the test weight below which oats would be discounted and a light blue arrow below which oats would be rejected. When analyzing individually, increasing nitrogen rate reduced test weight at Scott, Melfort, Yorkton, and Indian Head. No significant effects could be detected at the remaining 3 sites. While the phenomenon of falling test weights with increasing nitrogen is well known for oats, I've not seen a confident explanation for its occurrence. But I wouldn't be surprised if it's related to tillers forming more of the yield as nitrogen rate increases. A combined analysis found nitrogen management had no significant effect on oat test weight. When analyzed on an individual site basis, Swift Current was the only site where test weight was significantly affected by nitrogen management, but the effect differed between the total nitrogen levels. At Swift Current, applying UAN at the boot stage provided the highest test weight at the 110 pound per acre level of N fertility, whereas the highest test weight at the 140 pound per acre N level was achieved when using ESN. While this is a desired result, showing test weights were maintained by nitrogen management, the effects were inconsistent between the N levels at Swift Current. Moreover, none of the N management treatments at the other sites significantly increased test weight compared to just sidebanding all the nitrogen at seeding. Conclusions. Yield was maintained between levels of nitrogen management at all sites but Indian Head. At this site, applying a portion of the total N as ESN or UAN significantly decreased yield. In addition, a significant decrease in grain protein also occurred when UAN was applied at the boot. These yield and protein losses at Indian Head may have been the result of an excessive delay in nitrogen release from the ESN, or environmental conditions after UAN applications that were conducive to ammonia loss or stranding of nitrogen in dry soil. These highlight the environmental risks associated with split applying nitrogen. While there were a few instances where grain protein and test weights were maintained by nitrogen management, they were rare and inconsistent. Beneficial effects of nitrogen management on lodging were not detected despite high levels of lodging at 2 of the locations. It doesn't appear that grain protein, lodging, and test weight can be consistently managed by delaying access to nitrogen, either through using ESN or dribble banding of UAN. Thanks to Oats for supporting this project and for Sustainable Cap for funding it.